looking at the 2016 December Gold Problem 3, Lasers and Mirrors. And so in this question, Farmer John's cows are going to be running a laser light show. And so they're going to have a laser at one of the points in a 2D plane of Farmer John's farm. And they're going to point the laser so it sends out a beam of light. And on the farm, there are going to be various other fence posts where they can put mirrors to redirect the laser. And so on another coordinate, there's going to be a barn somewhere on the farm. And we want to find the minimum number of mirrors needed in order to get the laser light to the barn. So before we start this question, there's an observation we can make about the mirrors. And what we're actually going to notice is for any mirror, let's say this one here, then if I have a different object with the same X or with the same Y, I can reach it from this mirror. So what this means is if I have this mirror here, then depending on which way I tilt it, then it can reach one of these objects, and it can reach one of these. And so what we're actually going to be able to do is, knowing that every mirror can reach any object with the same X or the same Y, we can actually turn this into a graph problem. And when we turn it into a graph question, then we can create edges between any two nodes or objects that have the same X or have the same Y. So in the example test case, what this is going to look like is if we have the laser as 0, then we have node 0 here. And then node 0 has the same X as 3. So we're going to have 3. It has the same Y as 1, so we have 1 here. And then we see node 2 over here is going to have the same Y as 3. And then the same X as 1. And then 5 over here is going to connect to both 3 and 2 because they have the same Y. And then 4 doesn't have any connections with anyone. For example, this 4 here is never going to be able to be reached because it doesn't have any nodes that are either with the same X or the same Y. Since the lasers can only go in one direction, like this, no matter what we do, we're never going to be able to reach this here because we will never be able to do something like this, where a laser stops midway, or something like this, where a laser suddenly stops here. And so what we know is if they have the same X or the same Y, then we can definitely reach them from the current node. And if not, then we cannot reach them. And so what we're actually going to do in order to find the shortest path is we're going to use a BFS on this graph here. And when we do a BFS, it's going to give us the shortest possible route from our laser to our endpoint. And then the number of nodes we pass through is just going to be the number of mirrors. So if we go from here, down here, this is going to be one of our mirrors, go down here, reach here. So let's go look at the code for this question. So the first thing we're going to do is read in our input. And what we're actually going to do is we're going to have a couple of data structures. We're going to have our unordered maps, or ordered, that are going to be X same and Y same. And so they're going to map the X coordinate to the different fence posts or barn or laser that has the same X coordinate. And then we're going to have Y same, which is going to map the Y coordinate to the different objects with that Y coordinate. And for this, because we're going to use a BFS, I'm going to have a priority queue. And in addition to our priority queue, I'm going to have is X and is Y, which I'll go over later. But for now, what we're going to do is we're going to finish reading in the input. So after we read in the laser and the barn, we're going to push back into the X same and Y same for each one. And then we're going to read in our fence posts and update the X same and Y same. So the way this is going to work is the first index is going to be the X, the second the Y, or the first the Y, the second the X. And then in our priority queue, we're going to first push back our starting index or our laser. And so we're going to have is X and is Y here because when we pop something and we visit it from the priority queue, we're basically going to assume we're going to put a mirror on that fence post. And if we put a mirror on that fence post, that means if it came in from an X direction, it has to go out from a Y direction. If it came in from a Y direction, it has to go out in an X direction. And so what this is going to do is we're going to mark it as is X, which is going to be 1, or is Y, which is going to be 0. And then the next thing we're going to do is we're just going to loop through our priority queue. And so while our priority queue is not empty, we're just going to pop the top, and then we're going to have is an x, the coordinate, and then the actual value. And so the next thing we're going to do is we're just basically going to check whether or not it is the barn. And so if it is the barn, we're going to output the weight and then return 0. So that's going to be the end. And then if not, we're going to insert into our visited. And so our visited is just going to be a set of pairs, and we're going to insert whether or not it is an x and the coordinate. And then what we're going to do is we're going to look at the adjacency nodes, so the other nodes that we could possibly visit from this current fence post, or our location. And so if it is an x, then we're going to loop through the y's in our xsame. And so in this case, we're just going to push back the val plus 1, because one more mirror, and then we're going to push back is y. And if it was a y, we're going to loop through the ysame, and we're going to push back is x. And so this is just going to update our priority queue. And then at the very end, it's just going to output here. And so that's the end of our program.